Hi, my name is Ava Martino and I'll be presenting on Lab 3 of Physics 2211. In the introduction, I'll outline the purpose of the lab and introduce some key concepts used during the experiment. In the first part of the lab, I'll use my analysis of the star's motion to estimate the mass of the black hole by creating a computational model based on the star and black hole. In the second part, I will create a computational model to simulate the motion of a spaceship around the planet and moon. Finally, I will address the questions what if and what does it mean in the discussion. The purpose of this lab is to study motion under the effects of gravity. In this scenario, our system is a star, while everything beyond the star, such as gravity and black hole, constitutes our surroundings. For a brief preview, the mass of the black hole will turn out to be 1.3825 e to the 34 kilograms, and the initial velocity needed for the spaceship to not crash into the planet is 2.3572 e to the 4 and 2.3572 e to the 4 in the y direction, in the x and y direction. Some important concepts we used include gravitational force, which is the force of gravity that measures the attraction between two massive bodies. You can see the gravitational force formula on the bottom. We also use Newton's second law, which is when the acceleration of the object is directly proportional to the net force acting on the object and inversely proportional to the mass. And the F-net perp and F-net parallel equation, which is F-net is equal to F-net perp plus F-net parallel. We also use the position and velocity update formulas as well. Here's a video of the star's motion around the black hole. So for the initial conditions, the star's mass was set to 2.0 e to the 30, and the delta t was set to 86,400. To find the net force, I calculated the change in momentum over time. Then to find the mass of the black hole, I used the gravitational formula and isolated the black hole's mass. Then I found the perpendicular and parallel forces using the F-net equals F-net perp and F-net parallel equation. And then I represented them as arrows in the simulation. Here is my result for part 1, where you can see how the arrows got larger as the star became closer and closer to the black hole. So for the initial conditions for part 2 of the lab, the gravitational constant was set to 6.7 e to the negative 11, the mass of the planet was set to 8 e to the 27, the mass of the moon was set to 6 e to the 25, the mass of the spaceship was set to 7 e to the 12, and delta t was set to 60. So to find the net forces acting on the ship and moon, I used the gravitational force formula. Then I used these net forces to find the velocity for the planet and ship. I then used the position update formula to simulate the motion of the ship and the moon. Finally, in order to get the objects to move, I had to predict the initial velocity of the ship that would allow it to orbit around the planet. I found the ship's speed to be 2.3572 e to the 4 in the x direction and 2.3572 e to the 4 in the y direction. Here are my results for part 2. There might have been a few errors, such as a miscalculation for the initial velocity, or maybe something in the code. Now, what does it mean? How is parallel and perpendicular components different from the rate of change of momentum? While they are both mathematically similar, however, for F-net you would need the outside factors that are exerting a force on the system, and for rate of change of momentum, you need the system's change in motion. Now, for the what if question, how do I predict the motion of the entire system? So to find this, you would need to find all individual forces on each object in the entire system. For example, you would need to find all forces being exerted on the star, or all forces being exerted on the moon, or all forces being exerted on the black hole. And depending on the object in the system, some interactions may be more dominant than others because of their individual masses, like the mass of the black hole, for example.